Hello guys, let's solve another problem related to insulator string and string efficiency. So in this problem, we are given an insulator which supports a line, and this insulator is made up of three insulator discs. Usually in transmission lines, we use porcelain or glass material to manufacture discs, and then we connect various discs to form a string. And this string actually supports the transmission line, supports the conductors in transmission line. So if we draw the conceptual diagram of our transmission line, looks like this, where this is our tower. Then we have disc insulators, and then we have line. It's supported by by this by this string, which is made up of disc insulators, and its electrical equivalent diagram will look like this. This is our power, and here we have three discs. So each disc is represented by its self capacitance C, and then we have line. And also, naturally, we will have another capacitance between the tower and the node between the connection of two disks here and also one here. We call this as CE, earth insulator, um, earth capacitance. And this is C. And as all the disks are generally identical, so the capacitance of each of them is equal. Then the voltage from the line to the tower is our phase voltage, V phase. And voltage across each disk is different. So we will label them as V1, V2, and V3. Okay. Now in the statement, it is given that the potential across the top unit and the middle unit are 8 and 11 kilovolt. So which means respectively, which means the top unit has voltage of 8 kilovolt, middle unit has voltage of 11 kilovolt. So this is 11 kilovolt. And in the first part, we need to calculate the ratio of capacitance between pin and earth, which is CE, and self-capacitance of each of the unit, which means we need to calculate ratio K equals to CE over C. Okay, so we will apply circuit analysis techniques to solve this problem. In order to apply circuit analysis technique, we can either apply Kirchhoff's current law KCL or Kirchhoff's voltage law KVL. So now we name this node as A and we name this node as B. Okay, and the currents flowing through each of the insulator, through each of the capacitance, we can label them as, this is, let's suppose I1, and this current flowing here through the earth capacitance is I1 bar, and this current flowing through the middle capacitor is I2, and this current flowing through this earth capacitance is I2 bar, and this current is I3, and this current is I3 bar. Okay. Now if we apply KCL at node A, KCL at node A. So according to Kirchhoff's current law, sum of entering current must be equal to sum of leaving currents. We can see that entering currents are, as you can see, this is entering current I2. I2 is equal to, this is one leaving current and this is another leaving current. So they will be I1 plus I1 bar. And according to Ohm's law, we know that current is equal to voltage over impedance. And here we talk about the capacitances, so we will say capacitive impedance. And capacitive impedance in phasor form can be written as 1 over j omega c. Okay, so current therefore will be V multiplied by j omega c. Okay, that will be our current. Therefore, we can write I2 is equal to the voltage across the insulator, voltage across the capacitance through which I2 is flowing, which is V2, and the capacitance of this insulator, which is C. So I2 will be equal to V2 multiplied by j omega C. And similarly, I1 is the current flowing through the top insulator, and the voltage across the top insulator is V1. So V1 and j omega C. And I1 bar is the current which is flowing through the top earth capacitance, and the voltage across the top earth capacitance will be equal to V1 because this top earth capacitance is in fact in parallel to the top disk insulator, across which the voltage is V1. As you can see, this node and the other node, they are connected together, as the whole tower is at ground potential, is at same potential. So this one can be written as, but the capacitance CE, as we wrote here above, CE can be written as K times C. That is, CE is equal to K times of the self capacitance. And in the first part, we need to find K. So here we are going to write V1 j omega K times C. Okay. Now we can see we can cross some common terms, which are j omega C, j omega C, j omega and C. Okay. This will lead to V2 is equal to V1 plus K times V1. And if we rearrange this equation, K is equal to V2 minus V1 divided by V1. And we are given the values of V2 and V1. So V2 is 11 and V1 is 8 divided by 8. This is 0.375. This is what was required in the first part. Now, in the second part, or part B, we need to find the line voltage, okay, which is the voltage between two lines. So if we are able to find the phase voltage, okay, then we can simply multiply it with square root of 3 to get line to line voltage or line voltage. And phase voltage is equal to V phase is equal to V1 plus V2 plus V3. Okay, and further we will use V line to line, or V line is equal to square root of 3 times V phase. Okay, so in order to get V phase, we need V1, V2 and V3. V1 and V2 are given, but we need to determine V3. In order to determine V3, we will apply KCL at node B. At this node, we will apply KCL again. So KCL here will be equal to I3 is the entering current at this node. So I3 will be equal to sum of the leaving currents, which are I2 and I2 bar. So I3 is equal to I2 plus I2 bar. Okay. Again, we will apply the same rule as earlier to determine the currents. So I3 will be equal to V3 multiplied by j omega C, as the capacitance is C, and I2 will be equal to V2, that is the voltage across the middle insulator, multiplied by j omega C. Now for I2 bar, we need to see what is the voltage across I2. As we can see, between node B and the tower, the voltage is in fact the sum of voltage V2 and V1. We will have exactly the same voltage across the earth capacitance, because earth capacitance is in fact parallel with the C and the C. So plus, so we will add their voltages V1 and V2. That will be the voltage across this insulator. So plus V1 plus V2 multiplied by the, and the capacitance of the earth is K times C. Okay, and we also have j omega. Now we will see which of these terms can be cancelled. J omega C, j omega C, and j omega C can be cancelled. So V3 will now be equal to V2 plus V1 plus V2 multiplied by K. Now we will put all the values. We have the value of V2, V1 and K. We determined K in part A. So we will get V3 equals to 18.12 kilovolt. That will be our V3. Now, as we have found all the voltages, so we can find the phase voltage, which will be equal to V1 plus V2 plus V3, and after we plug the values of all the voltages, so 8 plus 11 plus 18.12, so we will get phase voltage equal to 37.12 kilovolt. Now our line voltage V line will be equal to square root of 3 times V phase, which will be approximately 64.29 kilovolt. Now in part C, we need to determine the string efficiency. String efficiency is equal to phase voltage across the string divided by n times the V3. So phase voltage is 64.29 divided by n is 3 times V3 is 18.12, and in order to convert it into percent, we need to multiply it with 100, and we will get, after solving this, we will get string efficiency. Sorry, here we will use the phase voltage, not the line voltage. So phase voltage is 37.12. So 37.12. So our string efficiency will be equal to 68.28%. Okay, that completes our solution. Thank you.